Okay. Hi, everyone. I'm Dr. Abigail Frost, and it's been a pleasure to give you a talk today about some of the work I do and how we can use the infrared wavelength regime to study a bunch of cool things in space. As I said, I'm Dr. Abigail Frost. To tell you a little bit about me before I begin, so currently I'm in Chile doing research today, but I usually work in Belgium at the University KU Leuven that you can see at the bottom there. And originally, as you might be able to tell from my accent, I am from the UK. And today I'm going to tell you about a bit about the work that I did during my PhD in the UK and also during the work that I do now, which looks to answer the question, how do giants form? Where do the most powerful and the biggest stars in our universe come from? So in my background, you can see this beautiful, colorful picture. And this is a picture of what we call a nebulae, or a star-forming region, a kind of nursery where stars are born. And you can see kind of two different materials in this picture. You can see these kind of dark folds, dark clumpy folds, and this is interstellar dust. And you also see plumes of illuminated material, and these are gas, and this is gas. And these are the two ingredients of stars. All stars in the universe are formed out of these clouds of dust and gas. But how do we get from a big extended cloud like this to a little star like you can see scattered across the picture? Well, the gravity is the key. And gravity is a force that acts on anything that weighs something, anything that has mass. And the story goes that Sir Isaac Newton, an English mathematician and physicist, started thinking about gravity after he was sitting under an apple tree. An apple fell on his head, and he wondered, well, why did it fall on my head? Why didn't it go sideways or up or do something else? And he basically worked out that the reason the apple fell down onto his head is because it was being pulled down towards the center of the Earth. And the Earth is a huge body. It has a lot of weight. It has a lot of mass. And so it exerts a strong gravitational pull, which pulled the apple down and also keeps us walking around on the surface of the Earth. And gravity is what also holds all of the planets in the solar system around the sun. So you can see our Earth orbits around the sun, and the reason it orbits around the sun is because the sun is even bigger than the Earth, has a stronger gravitational pull, and so the Earth is being held in this journey around the sun by gravity. And gravity is key to forming stars as well. So what I'm going to show you here is just a computer simulation, and this was developed by Professor Matthew Bate from the University of Exeter. So what we're looking at here is a very simplified spherical ball of this dust and gas. And so when we switch gravity on, we instantly see that there is this kind of compression, and all of the material in this cloud is sort of flattening out and clumping together under this force of gravity. And the color scheme here is anything that is kind of a darker color is colder, and anything that's a warmer temperature is a kind of a lighter color. So what you're seeing here is that this cloud is like collapsed into lots of different filamentary structures. And these are kind of the first aspect of this collapse, these long, skinny filaments. And along these filaments, you can see brighter regions, and then you'll see white dots popping out of those brighter regions. And these are stars forming out of cores along these filaments. And so all of this collapse happens because gravity is drawn to areas with more material, and this kind of creates a cascade of different collapses which take that big cloud and turn it into these little stars you can see popping up all over the diagram here as these white dots. So all stars form out of these star-forming nebulae, or these clouds of dust and gas. However, the kind of life cycle of the stars that form out of it can differ depending on their size. So most stars in the universe are like our sun, or what we call low-mass stars. And they will all follow a very similar kind of life cycle. So the main life stage of a star, which our sun is currently in, is called the main sequence. And this kind of phase is the longest phase of the star's life. And our sun will kind of keep ticking along in this main sequence stage for several billion years. Eventually, it will swell into a red giant. And the reason this happens is because what is happening on the inside of the star. So our sun generates light and heat that sustains almost all life on Earth. And the origin of that heat and light, that energy, is a process called fusion. So in the center of the star, you have very, very, very high temperatures and pressures. And so the tiny little molecules that make up the core of our sun are kind of flying around and being pushed together. Like the temperatures give them so much energy that they're zipping around so quickly that occasionally they can hit into each other so fast that they stick together and they fuse. And this is the process called fusion. And this fusion process releases huge amounts of energy, which generate this, the light and heat that we see as starlight and sunlight. Now, at some point, the material that's being thrown together, which is mostly what we call molecular hydrogen and sometimes a bit of helium, eventually this runs out, and we get a kind of a lack of that fuel to continue this fusion process. When this happens, the star begins to become a bit unstable, and it swells into this red giant phase. And the star cools at this stage. It becomes a bit redder in color. Kind of the redder you are, the cooler you are, and the bluer you are, the hotter you are when it comes to stars. And eventually it'll become so unstable that it can't really keep a hold of its outer layers anymore. And these start to be thrown out into space. And these create beautiful structures called planetary nebulae. Nothing to do with planets. It's a bit of a bad name, but that's what they're called. And some of the material from these planetary nebulae can be thrown out into space and can eventually feed into these kind of clouds and dust and gas that are forming stars. And so it's kind of like a cycle. Once all of the outer material is destroyed, you are left with the very core of your original star, which is very hot, leftover kind of remnant, which we call a white dwarf. And eventually this will cool down over billions and billions of years until it becomes invisible and of course becomes a black dwarf. Now, this is what the life cycle of our sun and stars the kind of same size as our sun will follow. However, stars that are at least 8 times the size of our sun, that we call massive stars, live very different lives. So massive stars are often bluer because they're hotter than stars like the sun, and they burn through their fuel supplies in that fusion process much, much faster than stars like the sun do. So instead of living for billions of years, they live only millions of years. And so once they've gone through that main sequence life stage, they then swell into red supergiants, which are much, much bigger than the red giants associated with sun-like stars. And eventually they can go through these cataclysmic explosions called supernovae. And supernovae are some of the most energetic events in the universe. So if you were looking, so we live in a galaxy called the Milky Way, a big collection of billions of stars. But there are also galaxies outside of our own Milky Way, which are other collections of billions of stars. And if a supernova goes off in another galaxy, that one star exploding as supernova can outshine the entire other galaxy to us. So this is really how much energy is happening. This is like a crazy, crazy phenomena that happens. At the end of a supernova, you're still left with like a remnant. You're left with either a neutron star, if it's kind of less massive, or a black hole, if it's really massive. And black holes, their gravitational pull is so strong that even light can't escape from them. Really like the heaviest objects in the universe. And also when that supernova happens, material can be thrown out again, and this can also feed back into those star-forming nebulae, these clouds of dust and gas, and help feed future generations of stars. Now, if you look up at the night sky, if you manage to get away from the streetlights or it's not a cloudy day, then you'll be able to see a bunch of massive stars just looking up. And I want to bring your attention to a constellation in kind of the center right of this photo here, which has the constellation Orion. And Orion, the ancient Greeks thought he looked a bit like a kind of a warrior. So he has his arm, maybe a shield, maybe a sword or something. And then in the middle, he's got 3 stars in the middle, which are Orion's belt. And within the constellation of Orion, you can see a number of massive stars. And I want to draw your attention to this one in the top left here, in one of his shoulders. And this is a star called Betelgeuse. And here we can see a picture of Betelgeuse that was taken with a telescope called ALMA. And this telescope is in Chile, and I'll talk a bit about telescopes in Chile later. But I just wanted to show you this to show you to give you an idea of the scale of how big these massive stars are. So what you can see here are these white rings, and these white rings are kind of the sizes of the orbits of planets in the solar system around the sun. So the Earth is a huge number of meters away from the sun, probably like 10 to the 11 meters away from the sun, and Saturn is even further than that. And so what you can see is just one star is taking up a lot of space in our solar system. It's bigger than the orbit of Jupiter around the sun. So this is really, really huge, huge objects, huge stars. So why should we care about massive stars and their formation? What do they do? Well, massive stars are really important for a number of different reasons. I already mentioned before that massive stars, when they go supernova, can outshine whole galaxies. But even when they're not in that kind of extreme phase, they still do a huge amount, they'll still create a huge amount of radiation, a huge amount of energy, and this can help us learn about other galaxies. So massive stars are less common than low mass stars, and I'll talk about that a little bit more in a minute, But they're so much brighter, and we're kind of on average around 1,000,000 times brighter than our sun, that if we look at a galaxy far away where we can't resolve the individual stars, most of the light that is coming from that galaxy of billions of stars is coming from the few massive stars that are in there. And so by looking at massive stars and understanding them and how they behave, we can understand a bit more about these distant galaxies. Another thing that massive stars do is they create huge amounts of energy, and they have these huge stellar winds. So here you can see an image of our sun, and hopefully you can see a bit of like material being thrown out in the bottom left of this movie. And this is kind of just an ejection of highly energized material coming away from the sun. And when that material interacts with our atmosphere here on Earth, we get a beautiful phenomenon known as the northern and southern lights, which happens when all those kind of charged particles from that windy material thrown off of our sun interact with the particles in the atmosphere that surrounds our Earth. And massive stars throw off this sort of material as well, but they do it much, much more, and the particles have much, much more energy. And what these winds from massive stars can do is they can even have the power to completely change the shape and distribution of material in star-forming regions. And so they can stop it, they can start it, and they really have a huge amount of influence. Another really important thing that massive stars do is they make a lot of what we call heavy elements in the universe. So to astronomers, we call anything heavy anything that isn't hydrogen or helium. And hydrogen and helium are kind of the smallest, simplest particles that we have in space. And most stuff in space started off forming from hydrogen and helium. But everything that we find here on Earth, so, you know, the carbon that might be in your pencils, the oxygen that we breathe, the iron in our blood, all of these were made in more massive stars. And so essentially, in order for our solar system to exist, for all the cool minerals and all the cool complicated materials that we find on Earth to exist, a massive star had to go through a supernova explosion, create all of those, feed them into a massive star forming region or a cloud of dust and gas, and then we are formed out of it. Our solar system formed out of it, and our planet, which can support life, formed out of that solar system. So basically, if we want to find out more about ourselves, in a way, we have to find out more about massive stars. So if I go back to this picture where I showed you the two life cycles of these stars, you'll notice that I didn't talk in detail about one specific stage, which was this one here, the protostar stage. And essentially, this is because this is what my work focuses on. I look at forming stars in these kind of clouds of dust and gas, and I try to work out why are massive stars living such different lives to sun-like stars when they're forming out of this same material. So what happens in this protostar stage? Well, I've got a little cartoon which kind of describes it, and I'm going to go through each box and hopefully explain everything. So in number one, we have a very simplified cartoon version of that kind of cloud of dust and gas, that molecular cloud. And within this molecular cloud, it's not all even, the material. No, it's not beautifully smooth. There are areas which have a bit more material and areas that have a bit less material. And the areas that have more material have a bigger gravitational pull. And so they pull more material towards themselves and begin to grow. And when they reach a certain kind of size, they collapse under the force of gravity, creating what we call a core. As this core shrinks in size, it becomes kind of thicker, all the materials push closer together, and it's more difficult for heat to escape, so it begins to heat up. And eventually, the central-most region is going to become a star. So this is the first kind of step towards creating a star. Another thing to know about these cores is they're not completely static in space. Everything is kind of moving a little bit. Everything has a bit of rotation. And so as the core gets smaller in size, it speeds up in this rotation to conserve what we call angular momentum. And an easy way to explain this is this: if you go to a pizzeria and you see the person making the pizza, usually they start off with a ball of dough, and then they will throw that ball of dough in the air, and then it will spread out into that pizza shape as they throw it and throw it. And so essentially what's happening is the rotation is increasing and material gets spread out into this pizza shape. And this is what's happening in number 3 of this cartoon. So you'll see that we've got this disc or this pizza shape of material, and that's happening because of this kind of shrinking of the core and this increase in velocity to conserve this angular momentum and create that pizza. So you have this disc forming. In the very center, you have the hottest region, which is your protostar. And you also have some remaining material from that core, which we call the envelope. And this material can be shrinking onto the disc and helping it to grow. And also we have what I've labeled as bipolar outflows. These are the 2 yellow regions coming off of the center of that disc. And we think these are also there to help conserve, kind of balance the forces happening within this, this core. And also all the kind of high energy radiation that's coming from that hot center is being channeled through and creating these kind of flows out of the disk. Eventually, the surrounding dusty material or that envelope will dissipate. You'll either have fallen onto the disk, or it might have just, if it wasn't close enough, might have just drifted away. And you'll be left with your central forming protostar, your disk, and that outflow that's happening. And this disk, which we sometimes call a protoplanetary disk, will also be feeding material onto the central star and helping it to grow through a process we call accretion. And when these accretion events occur, sometimes not all the material successfully gets onto that protostar, and you get ejection events as well. So you get these plumes of material coming out of the poles as well. Now, eventually accretion stops, no more material is being fed onto the star, and you're just left with this protostar, which is very, very close to becoming a main sequence star, like kind of that main life cycle of the star. And you've got that disk surrounding it. Now, in the same way that the molecular cloud wasn't kind of uniformly dense, it wasn't just completely smooth. This disk also isn't going to be completely smooth. And so wherever there is slightly more material, that will again attract more material to it under the force of gravity. And so you can get pockets of material forming, which can eventually form planets, and we call those planetesimals. Now, eventually, the central protostar is going to become hot enough to start that fusion process I mentioned earlier. It'll start throwing those molecules together and start releasing all this energy and start shining like a star or like our sun. And when that happens, the radiation from the star can usually just blow away any remnants of the disk, and any planets that had formed that were big enough to survive that will remain, and you'll have a little solar system like we do here. And it's a really interesting time for astronomy right now, and especially for us people who care about star formation, because we're now getting to the point where we can observe all of these lovely phases. So we can see these molecular clouds with its cores, we can look at individual cores, we can see these plumes of material, those outflows, we're beginning to look at these disks, we can see structure in these disks, and we're also being able to detect planets around these forming stars as well. But there's only one problem with this picture, and this is that we only know that this applies to low mass stars. We don't know if this applies to massive stars, and those are the stars that I'm studying. So why don't we understand as much about massive stars and how they're forming as we do for low mass stars? Well, there's a number of reasons why this is the case. So, and the main reason is because massive stars are more difficult to observe, and there are a number of reasons why this is the case. So for low mass stars live longer lifetimes, they evolve more slowly, and this is the same for their formation. You know, it takes much, much longer. It takes maybe like 1 million years for a star like our sun to form, but it takes kind of only 100,000 years for a massive star to form. And because of this, at some point in the low mass star formation, I mentioned that dusty envelope that was kind of surrounding the disk disappears. But for massive stars, we don't have that luxury, because the formation process happens so quickly that envelope's always in the way, like creating basically a veil of dust that we have to look through if we want to see this formation. Another problem is the short lifetimes of massive stars and how quickly they form, because this makes them rare. If something happens very quickly, you're less likely to see it. And this makes it more difficult for us to find examples of these forming stars, massive stars, and to see how they're forming. And another problem with this kind of fast lifetime is that it makes these stars statistically more distant. We are kind of on the edge of the galaxy, as you can see in this artist's impression that I've got on the right here, and there's a lot more galaxy far away from us than there is close to us. And so this means that if we do happen to find one of these massive forming stars, it's just more likely that it's going to be further away from us, and therefore more difficult to look at with our telescopes. And so in order to overcome all of these problems, we need really powerful observations. We need to use really powerful telescopes to study these massive forming stars. So when you decide you want to study something in space, you then need to think about how you're going to observe it. Like, you need to plan your observation, essentially. So the first thing that you need to decide is what wavelength do you want to observe in? And essentially what I mean by that is, what kind of radiation do you want to look at coming from your source to study it? Now, radiation can take many different forms. There's visible light, which is the kind of radiation that we used to see. There's infrared radiation. So if you're ever making toast and you see the kind of like orange bars heat up that are like toasting your bread, the heat that you're feeling from that is kind of what we call infrared radiation. We also use microwaves to cook food. We use radio radiation to communicate with each other. And we use X-ray radiation to look through our skins and muscles in medical practices to get images of our bones and things that happen inside our bodies. And so by using different kinds of radiation, we can also get different views of stars. And the general rule with observing is if you want to look at hot material in space, then you have to use short wavelengths, so something like X-rays or gamma rays, or ultraviolet rays. And if you want to look at very, very cold stuff, then you want to look at things like radio waves. And massive star-forming regions are very, very dusty. I mentioned those dusty envelopes that get in the way and make them and make these difficult to look at. But we can use that dust to study these objects. And we're lucky because this dust emits really, really well at infrared wavelengths. So the way that I study these sources is by using this infrared radiation. And here you can see a picture of our Milky Way in all the different kind of radiation that I just mentioned. So at the top, we have the radios, the very cool material in our Milky Way. At the very bottom, you see gamma rays, and these are the highest energy regions of our Milky Way. Above that, you see X-rays. Above that, you see optical or visible light. And above that, you can see some infrared radiation as well. And you can see that all of these different types of radiation gives a very different view of our Milky Way and anything we look at in space. So once you've chosen the kind of radiation you want to look at, the next thing to pick is what technique do you want to use? So probably the simplest or most intuitive form of observing is, you get your telescope, you go outside, you bend down, put your eye to the eyepiece, and then you look, and then your eye collects the light from the star you're looking at, and you use that to learn something about it. And kind of the more technical version of this is essentially imaging. You get your telescope, you point it at your star, and you use a computer, or you use a computer essentially to collect the light coming from the star, and then you can use that to learn something about it, make an image, or to look at the different types of radiation that are coming out of it. And so this is one way that we can look at massive forming stars. Another technique that I use is called interferometry. Essentially, the idea is with observing is the bigger your telescope, the smaller the details you can observe, and also the further away you can look into space. And interferometry is essentially like a little cheat. So instead of using one really, really, really big telescope, because there's a limit technologically on how big we can make telescopes, instead of doing that, we essentially use smaller telescopes, but put them very, very far away. And then we observe with all of those telescopes simultaneously looking at the same source. And then we combine the information that each of the telescopes gets to get information about the source. And by kind of putting these telescopes far away and observing at the same time, we simulate a telescope that is like the distance of these telescopes in size rather than just the size of the individual telescopes. So you basically simulate a very, very big telescope with this kind of technique. And so essentially what I do in my work is I combine infrared imaging and infrared interferometry with computer modeling, and I put these three together to tell me something about these massive forming stars. And so based on my work, this is kind of a cartoon of what we think is happening in these massive forming star regions. So essentially what we have in this cartoon that I've made to describe what's going on is in the very center, you have that massive protostar. That thing is eventually going to become one of these massive stars. Surrounding it, you've got this big dusty envelope of material. And the interferometry, which probes the smallest details, resolves disks within these systems. And these disks are rotating and feeding material onto the central star, and also are being fed from the envelope. So there's this constant stream of material, which is helping these stars to grow and become more massive. And also the imaging shows that we also have these really nice bipolar alphas. So the star, or the protostar, is funneling off lots of high energy radiation. This is carving tunnels out of that dusty envelope. And the imaging captures kind of like the reflection of the protostar's light, if you like, against these tunnels. And we can see that as well. And if you remember back to the star formation cartoon that I showed at the beginning, you may remember this is quite similar to that stage, the kind of early stages of low mass star formation. And so these massive stars, even though they're forming kind of much, much faster than these low mass stars, there still is a lot of similarity, and they're going through a lot of the same processes. So this helps us to find exactly how the material is being piled onto these stars to help them to grow, and helps us to understand a bit better what exactly is happening in these clouds of dust and gas to make the most massive stars in our universe. I just want to finish by telling you a bit about kind of the telescopes that I use to do my work. So here you can see a picture of me in front of the observatory that I use, or the collection of telescopes that I use. And this is the VLT, the Very Large Telescope. And the observatory has two different kinds of telescope, which I'll tell you about in a second. The observatory is in Chile. So at the moment I'm in Chile, but I'm in Santiago, in the capital. And this observatory is in the north of Chile, in the desert called the Atacama Desert, near a city called Antofagasta, which you can see in the top there. And so if you want to get to the observatory, you have to hop on a plane and you have to fly up over all the mountains in the north of Chile and over the Pacific Ocean until you get to Antofagasta. Once you get to Antofagasta, you need to get into the middle of nowhere because the telescopes are built really remotely in the desert. We don't want any interference from anything, so the further away they are from anything, the better. And so after a 3-hour drive in a little minibus from Antofagasta, you eventually get to the observatory. And once you get there, it's really like being on another planet. It's all these kind of beautiful rolling, like orange hills. It feels very Martian. And here you can see kind of the typical view from the observing platform. And you can see a big layer of clouds in the background. And now those are settled over the Pacific Ocean. And this is actually a good sign. If all of the clouds are down there and they're not higher up, it usually means we're going to have nice stable conditions for our observing for the night. So here are the two telescopes at the observatory. On the left, we have the smaller telescope. This is called an auxiliary telescope or an AT. And here you can see the dome is open and you can see some kind of like metal structure poking out. And those are kind of, that's part of the telescope is actually going to be collecting light and helping us learn something about our sources. And this telescope's on the smaller side. So the mirror on the inside, which I'll show you in a bit, is only 2 meters. On the right, we have the other kind of telescope, the big telescope. This is the unit telescope or the UT. And the mirror of this telescope inside is around 8 meters. And you can see that here. So here you can see the inner structure of the telescope. So this is looking inside that kind of big silver dome that I showed you just a second ago. And so here you can see the giant mirror. This is 8 meters across. And what happens is the light from the stars will hit this mirror. It will bounce up. There's another small mirror up here. And then that small mirror will direct all that light into this tube. And that's where all the scientific instruments are that let us learn something about our telescope. And when I'm doing interferometry, I use not only, or I can kind of use multiple telescopes at the same time. So either all the big telescopes or small telescopes to look at my sources. Yeah, so here's a picture of the observatory at night. You might think it looks a bit light, but that's because there was a really nice full moon a nice full moon present on this night. And you can see the big domes are open and all pointing at different sources and observing them. And in the back, you can see a strange kind of yellow line coming out from the unit telescope at the back. And these are lasers that we use for guiding and can help us, particularly with extragalactic work. Here's another picture. So I took this picture from not the observing platform itself, but kind of down at the kind of place where we stay, where we sleep and eat our meals on a night before I started observing. And so you can see those lasers coming off of that telescope again, and you actually have 4 lasers. They might look like 2, but it's actually 2 and 2, and they're kind of close together. And yeah, so this was, again, being used for guiding and looking at very distant objects. And here's another picture. This was taken on a night where there was not a moon out, so it's very much darker, much darker sky. And you can see again those lasers from the telescope coming to point at the source. And across this picture, you can see a beautiful kind of like dusty structure with a kind of lighter bulge in the middle. And that's essentially the plane of our galaxy. So as I said before, we're kind of close to the edge of our galaxy-ish. And what we're looking to here is the central part of our galaxy, the brightest region. And that kind of dusty material in the way is kind of the dust in the arms of our spiral galaxy. They're kind of getting in the way. And it's really cool when you're out there because you really can see this structure with your eye. You don't need a telescope, you don't need a camera to see it. It's just there, kind of reaching across the sky, and it's really, really beautiful. And even looking beyond our galaxy itself, you can also see outside the galaxy, just with your naked eye. Here you can see my friend Chumbon, who is now a lecturer and teacher in Thailand, and he is pointing up towards 2 kind of fuzzy blobs. And these fuzzy blobs are actually dwarf galaxies, so kind of miniature versions of our own Milky Way galaxy that are orbiting around it under that force of gravity. And we call these the Magellanic Clouds because back in the past, I think people often mistook them for clouds. And so we can do a lot with the telescopes that we have, and it's all really exciting, but I just wanted to look to the future a little bit to tell you a bit about what the future of infrared observing and just observing in general is headed towards. So in the center, you can see the observatory that I was just talking about, the very large telescope, but another really big telescope is also being built at the moment. This is called the Extremely Large Telescope. And you can see that kind of a model of that on the left here. And it's going to be one of the single biggest telescopes we've ever had looking at space. And it's really going to completely change the view that we have of space. And if you're wondering what the thing on the right is, that's just the Roman Colosseum, just to kind of give you an idea of how huge this telescope is going to be. And this telescope is due to start hopefully observing in 2028. It's already being built. This is another mountain in the Chilean desert, or the Atacama Desert, and you can see they're already building the foundations. And so this really happening. I really can't wait until the telescope comes online and we get a whole new, different view of space like we haven't seen before. Another cool telescope, which is just kind of starting to become operational, is the James Webb Space Telescope. So this is a NAS Space Telescope, a NASA-based space telescope, which was actually just launched in December of last year. So here you can see it in the lab while it's being assembled before it was launched. You see this huge gold mirror, which is going to be collecting the light and feeding it to the instruments, which will help us learn about lots of different things happening in the universe. And here is the Ariane rocket lifting off with the telescope inside, going to put it into orbit. And since it launched, it's now been moving between, basically moving into its position in the solar system where it's going to start observing in space. And we've got some first images coming in from JWST. So on the left, you can see a little selfie that it took of itself, and you can see that mirror that I showed you that you could see in the lab picture before. And also you can see these two pictures on the right, which are kind of the first specks of light that JWST is beginning to see. And it's basically just trying to kind of, sort its head out, make sure everything's working okay, make sure it's going to be able to observe. And it's doing all these checks now. And very soon, hopefully, it will start observing. And it really is going to give us a really beautiful view in the universe, because from space, we don't have to worry about, clouds or the Earth's atmosphere getting in the way. So we're really going to have a really beautiful view of the universe with this telescope. And so with that, I'd just like to say thank you for listening. Just to summarize quickly, I've talked a bit about massive stars, why they're cool, from creating the elements that we're made out of to creating huge explosions and to lighting up whole galaxies. I talked about how they're kind of difficult to observe, so we don't really understand how they form. But also I've talked about how we can use different telescopes and different observing techniques to get new information on these sources and to probe the little details of them. And essentially how it's allowed us to find that there are some similarities between the formation of low mass stars and massive stars. So our sun and massive stars do really start in the same place and do go through some similarities as they're forming. And also it's really kind of looking like a bright future for studying everything in the universe, including these forming stars, because we've got a whole bunch of new telescopes about to start working and are being built, and it's really going to be an exciting time to get into astronomy. So with that, I'd like to say thank you for listening, and I will now take any questions. Thank you. Oh God, hang on. There we go. Cool. Whoa, got a lot of questions. This is looking exciting. Give me a second. Cool. Ben Young asks, why are those giants red when they are so bright? Good question. So the giants look cooler because if you imagine you've got something like a hot star that's small and then you spread that out over like a bigger region, basically the amount of heat coming out of the surface at any one point goes down because you're spreading it over a bigger area. And so it looks a bit cool. That's essentially what's happening. Okay, is there a lot of gold in these giants? Since their material must have collapsed a lot of time since the Big Bang. That's a good question. So this process of collapse takes a very long time, but it's not the collapse itself that is forming the fun molecules like gold or iron or the heavy elements. It's only in either these very big supernova explosions or other crazy things that stars can do, like merging with each other or doing other various complicated things that I didn't really have time to talk about. It's only through those processes that these things like gold get made. So these supernova or these strange interactions. It's not just from the material sitting around and collapsing that does that. So it's really once the star starts fusing and the star starts going through different, more energetic processes that these things start to get generated. Okay, what is the distribution of giant stars throughout the galaxy? Is it likely there are planets forming in very carbon poor regions and organics are out of the question in these systems? That's a good question. So let me read this question again. So I do think that you can have planetesimals begin to form, I think, in, carbon poor regions, I think. But whether, as to how long they survive, as to how likely we are to find them, because obviously like the most metal poor star forming regions will be in older galaxies, and so has something happened to them in the meantime? Have they been destroyed by their host stars? Because our own sun is going to expand and eventually swallow our inner planets. So could something like that have happened to these much older planets? I don't know. Essentially, I think there could be planets which have a completely different composition, but I don't know what might have happened to them since they were formed. But yeah, I mean, you can have different generations of planet formation. Our solar system is probably like at least a second generation system, because we have all these complex materials in them. But there's no reason why the collapse that would lead to the formation of planetesimals wouldn't happen, I think, in a different region. So it's my take. I'm not a planet scientist, but it's what I think. Okay. Is the rotation axis of stars that formed in the same cloud pointing in the same direction, or is the orientation of the protoplanetary disks random? This is a really good question. So if you have planets forming a disk, then we would think that most of their we would think that what we would call them would be coplanar. So that's what we kind of look at when we look at our own solar system. Most of our planets, apart from Pluto and some of the ones, some of the dwarf planets like Pluto, which are far out, have fairly kind of regular orbits. They're all kind of going in the same sort of elliptical journey around the sun in a similar-ish way. However, we are finding we are finding protoplanetary disks around other stars which are inclined in different ways compared to their stars. So our sun is rotating around the same axis as our planets, but that isn't the case in all of these systems. So it definitely isn't a strict rule, and we're trying to work out. We don't know exactly what has to happen to these disks in the first place to cause that misalignment, but it's an ongoing field of research. So yeah, it's a really interesting question, and yeah, hopefully we'll know more about that soon. Okay, is there a single control room for the VLT or one for each telescope? Okay, so we have a single control room, but there's kind of like stations for each telescope. So you have a station for UT1, Unit Telescope 1, Unit Telescope 2, Unit Telescope 3, and Unit Telescope 4. And they all have nice names, actually. They're all named after Mapuche words for different space objects. So the Mapuche were the indigenous people of Chile. And so, we have one of the telescopes called Yapun, for example, and they're all kind of named after different objects like Venus, I think, the moon, and various other things, which is cool. And so you have people controlling each of the telescopes from those desks. And then you also have, I think, a control center for the VLTI as well. But yeah, they're all just desks in one room. Everyone is kind of working together in one control room. So it's pretty nice. Okay, how strong are these lasers that the beam can be seen so clearly? Okay, so the reason they look so bright in the photos is because I was using like a special camera mode that allows me to, look at the stars, so they appear much brighter. But you can see them with the naked eye. It just, it's not super obvious. Like I remember I was just walking around outside, and then I was like, that's a weird like plain trail, and then I was like, oh wait, that's a laser. And then I was like, cool, I'm going to take some pictures. And then it is much clearer in the pictures that the lasers were there. Okay, what's the next big thing after the ELT? How much bigger can telescopes get? Good question. So the next kind of planned generation, at least for stuff on the ground, are these 30-meter telescopes. So the kind of the mirror of the ELT is going to be around 30 to 40 meters, but there's also plans for other telescopes that are that size, like the TMT, which we're trying to work out what we're going to put it at the moment. And so at the moment, because the ELT is in the southern hemisphere, we also want something similarly powerful in the northern hemisphere. So that's currently the plan for the TMT, because there's a small overlapping region, but like usually you don't get, my hands doing lots of things. Usually you can't see exactly the same sky from the northern hemisphere as you can from the southern hemisphere, so you want to cover all your bases. So yeah, another 30-meter telescope in the north is on the cards. And then also we're thinking about a bunch of fun stuff. So there are plans to have kind of different wavelength space telescopes that are as powerful as a JWST. A JWST is an infrared telescope, but there's plans to develop a kind of ultraviolet and optical telescopes that can match the JWST. I think Louvois is the name of that one that's currently being planned. And then there's also eventually plans for kind of potentially space interferometry. So instead of having multiple telescopes on the ground, you're actually having multiple telescopes in space, which can observe at the same time. Because interferometry from the ground or using multiple telescopes from the ground is already pretty tricky. This is like a big technological feat, but yeah, it's definitely something that would be super powerful if we eventually get to do it, and it's something that some people are talking about. So yeah, I think that's the last question. So thank you all for tuning in, and I hope the talk was interesting and that you learn a little bit more about space and how we take observations of space in the infrared. And thank you very much to everyone behind the scenes who's helped put this together. And yeah, have a great morning, afternoon, evening, depending on where you are. And thanks for listening. And if you have any other questions, you can always hit me up on Twitter at astro.frost. So cool. Thanks, everyone.